John, going through the Level 3 2022 Physics Waves exam. And the best thing for you to do is first work through the paper and then check my answers in the end to see if they match. All right, okay, question 1 is on standing waves. Jane enjoys playing the guitar. When she plucks a string, one of the resonant harmonics that is produced is shown in the diagram. What do we have to do? State which harmonic this is and label a node and an antinode. So this is the third harmonic, and nodes are points of no disturbance and antinodes are points of maximum disturbance. So I've just labeled all of them. Now the length of the guitar string is 0.645 meters, so that's that whole length is 0.645 meters. And the frequency of this particular harmonic that's indicated in the diagram is 995 hertz. We have to calculate the speed of sound through the string. So in order to get the speed of sound, we use the wave equation, V equals F lambda, but the first step is to find out what is the wavelength. How do you know what the wavelength is? Let's see how many half wavelengths there are in this one. So there's 3 lots of half wavelengths, and that makes up the length of this guitar string. So 3 halves is the same as 3 over 2 times lambda is 0.645. So your wavelength is 0.430 meters. If you've got that much, you achieved. And then speed is F times lambda. This is your F, that's your lambda. Multiply the 2, you get your answer. That's your merit. Next question. When Jane is playing this note of 995 hertz, her friend Melly tunes her guitar by playing the same note as Jane with the same loudness at the same time. And what happens is they hear beats. Then Melly tightens a guitar string so that the sound travels faster in the string until no beats are heard. So remember, when no beats are heard, then Melly's frequency would have become 995 hertz. So what was original frequency? The original frequency is 995 minus 5, which is 990. Why? Because when she tightens a string, the pitch increases, so she would have been at a lower pitch. Okay, now explain the effect that tightening of the string has on the frequency of the note. So when she tightens the string, the speed of sound increases, and that's stated over here. However, what is it that stays the same? The length of the string remains the same. So if the length remains the same, then the wavelength stays the same. Now this is your wave equation. The wavelength is the same, the speed's increasing, so frequency has to increase. That's a merit question. Moving on, Jane also plays the flute, which can be modeled as an open pipe, and Melly plays a clarinet, which can be modeled as a pipe that's closed at one end, open at the other. Explain why. That means it's excellence. Melly cannot produce the second harmonic on the clarinet, whereas Jane is able to do so. So here's a diagram of the flute, which is open at both ends, and here's a diagram of a clarinet, which is closed at one end and open at the other. The important thing is when it's open at both ends have to have antinodes, and between antinodes you need to have nodes. But however, the clarinet at the closed end has to have a node all the time and an antinode at the open end. So what happens to Jane, because she plays the flute and because she can produce all multiples of half wavelengths, and because the half wavelength is your fundamental, and it satisfies a condition of the flute by having antinodes at both ends. However, the clarinet is closed at one end, so it has to have a node at one end, and so you only have odd multiples of quarter wavelength that can be produced on the closed pipe. So the odd multiples are quarter wavelength, 3/4 wavelengths, 5/4 wavelengths, and so on. And if you've got till there, you get your merit. Just going a step further, in order to have these resonate, you need to have waves that fit the length of the pipe and also satisfy the conditions of the pipe. And what actually happens in order to get that standing wave, the reflected waves at a closed end undergo a phase reversal. so that you get your nodes, and there's no phase reversal at the open end. That's why you get the antinode there. Okay, if you said all this, you get your excellence. Moving on to question 2, interference. Vincent is studying interference patterns formed by diffraction gratings, and he has a set of diffraction gratings with different slit spacings. And what does he do? He shines a red laser through it and observes the pattern. Now describe the effect on the pattern of fringes that are formed on the screen when the distance d between the slits increases. So my thinking for this is you go for the equation. N lambda is d sine theta. When d increases, sine theta has to decrease. If sine theta decreases, then the angle theta decreases. So the fringes will be closer together. And if you have the fringes rather than far apart, you have them close together, so you get more of them. Next, he uses a grating with 6 times 10 to the power of lines per meter, so that's your capital N. He sees a series of bright dots that are maxima. So maxima is constructive interference, your antinodal lines. He measures an angle of 54 degrees between the third bright dot and the central bright dot. So this is your central bright dot. Then you got the first, second, third. So that whole angle is 54 degrees. So here we've got to calculate the frequency. So the little n, the order number is n, capital N, which is so many lines per meter, and your theta is 54 degrees. Step 1 is calculate d, which is 1 over n, so it's 1 over 6 followed by 5 zeros. And then I used n lambda is d sine theta to get my lambda, okay, or the wavelength. So you get that, and so the wavelength turns out to be 4.49 times 10 to the power of negative 7 meters. Then in order to get frequency, I need to use v equals f lambda, or f is v over lambda. So this is the speed of light, and there's your wavelength, and there's your answer. Okay, moving on. Now, then Vincent shines white light through the same grating with the same lines per meter, and he notices that when it's white light, the central antinodal line is white, and each of the orders produce a complete spectrum. Explain both observations using your knowledge of colors and wavelength of light. So white light is made up of many colors, and each of them have their own frequency and wavelength. So if you said so much, you get you achieved. The central antinodal line is where all the colors arrive in phase with 0 path difference, and they interfere constructively to produce white light. Each order forms a complete spectrum with blue on the inside and red on the outside. This is because each color has its own path difference, and it's different from the other color. So the path difference of blue will be less than that of red, so it's closer to the center, whereas red, which has a longer wavelength, will have a bigger path difference, and so that's further away. So if you said all this, you go all the way to excellence. And then this one here, while studying the effect of shining white light through a diffraction grating, he measures 28.5 degrees, so this is your violet light, and 50.82 for this red of the same order. So you got the different colors in between. So calculate the wavelength of red light, and then this is really important. The difference in the wavelength between red and violet is 2.54 times 10 to the power of negative 7. So begin your answer by identifying what's common to both red light and violet light. So this is how you do this. So n lambda is d sine theta. So this is lambda for red, and that's a theta for red. And also n lambda, where lambda is violet, is d sine, and this theta is different. So what's common to both? N and d are common to both. So n over d is for the red. It is sine 50.82 over the wavelength of red, and also this is the same as sine that over wavelength of violet. So we can equate those two together, and then I brought all the signs in one end, so that goes up and this one comes down, so you get this, and then you put sine 28.5 divided by sine 50.82 in your calculator, and you end up with this. Now what have I done? So instead of violet, I rearranged this and I took violet minus violet to this side, so you get wavelength of red minus 2.54 times 10 to the power of negative 7 equals wavelength of violet. So in place of wavelength of violet, I've got that. Divided by wavelength of red is 0.607, which is when I put that in the calculator, and then I'm just solving for wavelength of red, and you kind of get wavelength of red is here. So you just go through those steps. Okay, you kind of factorize there. Okay, moving on. Next one is Doppler effect. Okay, speed of sound is 340 meters per second. So there are two police cars. They have identical sirens of frequency 750 hertz. One is stationary and the other one's approaching Emma, who's standing on the curb. Now compare the pitch of the note that Emma hears to the pitch of the note that the driver hears as his car approaches her with the siren on. So the driver will hear the actual frequency of 750 hertz, whereas Emma will hear a higher pitch because it's approaching. That's achieved. Then the stationary car, as well as the car approaching Emma, sounds their sirens, and the frequency heard by Emma differs from the actual frequency by 8.50 hertz. So what are they talking about? They're talking about beats. Okay, so the frequency that Emma hears, so we've got to show that the speed of the police car is that much. So this is the actual frequency. Emma hears a higher frequency. How much higher? 8.50 higher than 750. So that's the frequency. That's the apparent frequency. That's your speed of sound waves. And then you use the Doppler equation, and this is how you solve for Vs. Okay, that goes to merit. Then Emma is standing very close to the side of the road as the police car approaches her and then goes past her at constant speed. By calculating the apparent frequency both times, when it approaches and recedes, we've got to draw the graph. So when it approaches, this formula, you get that much. When it goes back, you've got to add there. Okay, that is the frequency, actual frequency, wavelength of light, and then you got to add those two. And you get these two, and then what do we have to do? We have to draw the graph. So it is kind of steady, and then over here she hears the actual frequency of 750. Make sure it passes through 750. That's Emma standing. And then when it goes away, the frequency gets lower. So it's about 741. Okay, then explain the reason for the shape of the graph and comment on the shape as it approaches Emma and goes past her, and include a comment about the gradient of the graph. So as the car approaches Emma at constant speed, Emma hears a note of higher pitch, so that's a pitch, and this is a constant pitch, so the graph line has a gradient of 0. I'm talking about that part. Okay. And then as the car approaches very close to Emma, the pitch drops to the actual frequency. So the gradient is steep, and she hears the actual frequency when the car's directly in front of her. The graph line drops further as the car goes past her to a lower pitch as it goes past her at constant speed. So once the frequency that Emma hears has changed from 758.5 to 741.7, the graph line will again have a gradient of 0 as it travels at constant speed. So the gradient at this part and this part is 0, but this one is quite steep as it drops. And that's the wave